Welcome back. This will be the first of two lectures on section 4.4 from the textbook, Similarity and Diagonalization. Now I've broken this section up into three parts: an illustrative example, similar matrices, and diagonalization. I'll cover these first two parts in this first video lecture, and we'll cover diagonalization in a second video lecture. So let's begin with an illustrative example. Now let's begin by working this problem together. Let T be the transformation in the plane that reflects a vector through the line passing through the origin with direction 3, 4. Let's find the matrix of the transformation T. Now we encountered problems exactly like this back in section 3.6 when we first introduced transformations of the plane. Now back then in chapter 3.6, we would have done the following. We would have said, take E1 and E2, the standard basis for R2, and plug E1 into T and plug E2 into T and find their images. Those two images, the image of E1 and the image of E2, would form the two columns of the matrix of the transformation T. Now I want to look at this through a slightly different lens. Now the key idea here is to think about the transformation T acting on a more natural basis, a basis which is in a sense tuned to the transformation T. Now remember that our line is the line through the origin with direction vector 3, 4. And I'm going to let one of my basis vectors be the vector 3, 4. In other words, a vector that is on the line. The other vector I'm going to pick is the vector 4, -3. So these are the vectors u and v, and together they form a basis for R2. Now what's special about these two vectors is that they act in a very nice way with respect to the transformation T. Notice that u is already on the line, so when we apply t to the vector u, it remains unchanged. T of u is equal to u. On the other hand, v is orthogonal to the line, so when I apply t to v, it flips the vector, and so t of v is the negative of the vector v. So we have two vectors, u and v, under which the transformation T acts in a very simple way. T of u equals u, and T of v equals -v. Now let's go to the document camera and work out the matrix for this transformation using this very natural basis of the basis consisting of the vectors u and v. All right, welcome to the document camera. Now, to work this problem, we've got to get a few of our ducks in a row. So let's start here. Let x stand for a generic vector in the plane. And so let's say x has coordinates x1 and x2. And let's say script b is going to be the basis consisting of the vectors u and v in that order. So that's the vectors, let's say 3, 4, and 4, -3. So that's another basis for R2. All right, now the first thing we want to think about is this. How could I write this vector x, just a generic vector in the plane, how can I write it as a linear combination of these new basis vectors u and v? So let's think about expressing x as a combination, let's say a times u plus b times v. Now what is that going to look like? It's going to look like solving this equation. Now we know that we can express this linear combination of 3, 4, and 4, -3 through matrix multiplication. So one way to express this right-hand side is to write it as the matrix with columns 3, 4, and 4, -3 times the vector a, b. Now, I'm going to call this matrix, we're going to want to highlight this matrix. This is the matrix whose columns come from our basis vectors. I'm going to call that matrix P. And so it says if I want to calculate the relationship between A and B and the components of this vector x, they're related through this matrix multiplication. X is equal to the matrix P times the column vector AB. Now, we're really interested in the reverse relationship. Given X, how would I find A and B? And what this allows us to do is express that through the inverse of P. So if we want to find these components or these coordinates A and B, all we have to do is take the inverse of P and apply it to the coordinates or components of the vector x. And what that would look like is and this is not hard to find the inverse of this matrix. It turns out that it has entries 0.12, 0.16, 0.16, and negative 0.12. All right. Now, we'll need more of this later, but this is the setup, right? This is telling us that I've got a new basis in the plane, namely this basis in terms of these vectors u and v. Therefore, if I have a vector in the plane, I want to write it as a combination of u and v, so I want to find its so-called coordinates relative to this new basis. And what this formula is telling me is I can easily transform the coordinates of the vector x in its standard, with respect to the standard basis. I can go through this matrix P inverse and find the coordinates of that same vector relative now to this new basis. All right, so that's kind of a resting point for the first part of this proof. We know how to kind of go between these two different coordinate systems. Given a vector in the standard coordinate system, I can multiply that vector by this matrix and transform it into a vector in this UV coordinate system. Okay, so we have that ready. Now let's look at kind of the point of using this basis relative to this simple transformation. Here's the idea. So now suppose I've got my vector x expressed as a combination of the vectors u and v. The idea is to use the fact that t acts very simply on u and v, and t is a linear transformation. So if I want to know what t is at x, I can say, well, that's the same thing as t at au plus bv, but t is linear, and so this is going to be a times tu plus b times tv. And here's where the fact that this basis u and v is nicely tuned to our transformation. We know that t applied to u is just u. That's a very simple idea. T applied to u is just u. And t applied to v is just the negative of v. And so this looks like a times u plus negative b times v. Now let's do a little bit of work here. We know that this is a linear combination of u and v, and so I can write this as the matrix, in this case P, the matrix whose columns are coming from u and v, times the vector with components a and negative b. Okay, now I'm going to do one more thing. I'm going to think of this vector a negative b as the result of taking the vector with coordinates a and b and multiplying it by a very simple matrix. So let's rewrite this, just this part a negative b. All right, so let's make sure we understand what we've done here. If I just think about this last matrix multiplication, multiplying that simple matrix times the vector AB, I can see that I'm going to get A and negative B. And so all I'm doing is I'm taking this vector A negative B and I'm writing it as a simple matrix times AB. Now I'm going to do one last thing. I'm going to remind you that AB can be written as a matrix times the vector x. So let me do one last thing here. Okay? So this says that t applied to the vector x as this is the same thing as the product of these three matrices applied to the vector x. So whatever the product of these three matrices is, and I will show you in just a second, whatever that product amounts to must be the matrix that's representing this transformation t. So let me show you what the final answer looks like. After you multiply these all out, you're going to get negative 0.28, 0.96, 0.96, and 0.28. Okay? And so that's interesting. And one of the things I want to draw your attention to is, and this will be important as we go forward, the product of these three matrices, right? The product of these three matrices is equal to that matrix. So if I call this matrix A, this is the matrix P. I'm going to call this diagonal matrix D, and I'm going to remind you that this matrix here is P inverse. One important consequence of this work is that when I'm converting and I'm working through a different basis, a basis that's tuned to our transformation, we're always going to get a representation like this. In this case, we're saying the matrix for the transformation A can also be expressed as P times D times P inverse. And we can kind of attach meaning to this. This matrix P here is carrying the basis vectors for our new basis. The matrix P inverse is obviously the inverse of P, but we know how to think of that. It's the thing that's going to carry our vector in standard basis into a vector in the new basis. And so this is just translating. This is translating from the standard basis. It's taking a vector in standard form, standard basis, into a vector in the UV basis. Now, what is the meaning of D? Let's think about the meaning of D. This is important. You'll probably remember that this is the matrix of a simple reflection. This is the matrix in standard form. In a standard basis, we would look at this as the matrix of a transformation, a reflection through the x-axis. And effectively what we're saying here is that in this basis, in the UV basis, this is the representation of this transformation now in this new coordinate system, in this UV coordinate system. So we should really think of D as a representation of this same transformation now in the UV coordinate system. So this is kind of the UV representation of T, and this is the standard basis representation of the transformation T. So in effect, A and D are both representations of the same transformation, albeit in different bases. And so this is just a way of kind of describing that process. Translate from standard coordinates into UV coordinates, apply our transformation in the UV system, translate it back into the standard system, and that's the way we can think about the action of this single matrix A. All right, now let's head back to the class notes and continue. So let's summarize our work from this problem. We've got three important matrices that we've discovered along the way. First, the matrix A, which represents the transformation T relative to the standard basis vectors. The second matrix P represents the matrix that contains the basis vectors U and V. So this is the matrix of basis vectors. And then finally, the matrix D that represents the transformation T relative to these basis vectors u and v. So this is another representation of the transformation t now relative to a different basis, namely the basis given by the columns of P. And what we've shown is that A can be expressed as P times D times P inverse, and equivalently, by multiplying both sides on the right by P and both sides on the left by P inverse, we can write D as P inverse times A times P. So we can think of A and D being related to each other through these equations. Now, the thing to remember, though, is that A and D represent the same transformation, T, but with respect to different bases. Now, this brings us to the all-important concept of matrix similarity. Now, let A and B be n by n matrices. We say that A is similar to B if there's an invertible n by n matrix P such that P inverse times A times P is equal to the matrix B. If A is similar to B, we write A tilde B. A is similar to B. Now, let's go back to this defining equation. If we multiply both sides of this equation by P on the left and P inverse on the right, we can express that same relationship between the matrices A and B in this form. We can say that the matrix A is equal to P times B times P inverse for some invertible matrix P. And I actually prefer this representation of similarity. So I would say A is similar to B, provided that A is equal to P times B times P inverse for some invertible matrix P. And the reason I like this representation is because it's very suggestive, right? This would say that the matrix A is representing some transformation in the standard basis vectors for Rn. And B is representing exactly that same transformation. B is relative to the basis vectors, which are the columns of this matrix P. So in a way, what matrix similarity is suggesting is that there's an underlying transformation that's being represented once through the standard unit vectors, and that's A, and a second time through a set of basis vectors that are encoded in this matrix P. So both A and B are referring to exactly the same transformation, but through different basis vectors. And that's an important concept to carry with us as we move through this section. Now let's take a look at an example. Let A be this 2 by 2 matrix with entries 10, 12, -6, and -7, and let B be this diagonal matrix with diagonal entries 1 and 2. Now I claim that A and B are similar. Here's a matrix P with entries 4, -3, -3, and 2. It's easy to check that its inverse has this form. And it's also easy to check that when I multiply P times the matrix B times P inverse, that matrix multiplication results in the matrix A. In other words, we've expressed A as a matrix P times B times the inverse of P, and that shows that A and B are similar. Now let's take a look at theorem 4.21. Throughout this theorem, let A, B, and C be n by n matrices. So there are three statements. Statement A, the matrix A is similar to itself. Statement B, if A is similar to B, then B is similar to A. Statement C, if A is similar to B and B is similar to C, then A is similar to C. Now, statement A is really saying that matrix similarity is what's called reflexive. And statement B is saying matrix similarity is symmetric. And statement C is saying that matrix similarity is transitive. Now, typically, properties A, B, and C are the defining properties of what's called an equivalence relationship. And what theorem 4.21 is showing is that matrix similarity is an example of an equivalence relation. Now let's head over to the document camera and work out the proof of theorem 4.21. All right, welcome to the document camera. Let's look at the proof of theorem 4.21. Remember, A, B, and C are n by n matrices, and our first task is to show that a matrix A is always similar to itself. And this is actually a fairly simple thing to do. So for part A here, we're just going to remember that a matrix A can always be written as the n by n identity matrix times A times the inverse of the n by n identity matrix, which again is just another identity matrix. And so it's actually fairly simple. The matrix A can always be represented as an invertible matrix times A times the inverse of that matrix. And that shows that A is similar to itself. Okay, in part B, we want to show that if A is similar to B, then B is similar to A. Now, one way to think about A being similar to B is to say that A is of the form P times B times P inverse, where P is an invertible matrix. Now let's flip this around. Let's write B in terms of A. So let's multiply by P inverse on the left and P on the right. So this is the same thing as P inverse A P equals B. All right, in other words, B is equal to P inverse times A times P. Now what I want to do, and this is not completely necessary, but just to kind of help us get it into a form that's a little more recognizable as a similarity condition, let's let Q be the matrix P inverse. Then the inverse of Q is going to be the inverse of P inverse. But we know that the inverse of the inverse is just the matrix itself. So this is just the matrix P. So everywhere I see the matrix P, I can write Q inverse. And everywhere I see the matrix P inverse, I can write Q. And so this relationship here can be expressed as B is equal to Q times A times Q inverse. And that shows that B is similar to A. So A being similar to B implies that B is similar to A, because it can be written as A sandwiched between a matrix and its inverse. B is similar to A. All right, finally, let's go to property C, and this is the most interesting of the proofs. All right, so we know that A is similar to B, and B is similar to C. So let's see what that means. To say that A is similar to B means that I can write A as P times B times P inverse for some matrix P and its inverse matrix. I can sandwich B between a matrix P and its inverse. We're also saying that B is similar to C, and that means I can write B. I'm going to think of another matrix. Let's call it Q. B can be written as Q times C times Q inverse. I can sandwich Q between a matrix Q and its inverse and represent B that way. Okay, now I need to show that A is similar to C. And here's what we're going to do. In place of B here, I'm going to write Q, C, Q inverse. So I've just taken this relationship here, and in place of B, I've represented B using this similarity relationship. B is Q, C, Q inverse. Now I'm just going to reassociate. I'm going to think of this as P times Q times C times Q inverse P inverse. And I'm going to do one last thing. I'm going to recognize that this product of inverses, Q inverse times P inverse, can be written as P times Q inverse. Okay, so the inverse of a product is the product of their inverses taken in reverse order. So I'm just using that principle here. And now we're done. This is showing us that A is similar to C, because I can write A as a product of a matrix times C times the inverse of that matrix. A is similar to C. So this proves part C. A is similar to B, and B is similar to C implies A is similar to C. And so that brings us to a close here for our proof of theorem 4.21. Let's head back to the class notes and continue. Next, let's study theorem 4.22. Throughout this theorem, let A and B be n by n matrices with A and B similar. A is similar to B. Now in statement A, we learned that the determinant of A and the determinant of B are equal. So similar matrices have to have equal determinants. Statement B says A is invertible if and only if B is invertible. Statement C, A and B have the same rank. Statement D, A and B have the same characteristic polynomial. Statement E, A and B have the same eigenvalues. Statement F, A to the power of m is similar to B to the power of m for all integers m greater than or equal to 0. And finally, in statement G, if A is invertible, then A to the power of m is similar to B to the power of m for all integers m. Now, what I want to do is go to the document camera, and I want to pick 3 of these to work with you. We'll work through the proofs of 3 of these, and we'll work through A, D, and E together at the document camera. So join me there to look at the proofs of A, D, and E. All right, welcome to the document camera. We're going to look at the proof of theorem 4.22, and in particular parts A, D, and E. Let's take a look at part A first. We want to show that if A and B are similar matrices, then their determinants must be equal to each other. Now, to say that A is similar to B means that A can be written as P times B times P inverse for some invertible matrix P. Now, one property of determinants that we can use here is that the determinant of a product is the product of the determinants. And so the determinant of A can be written as the determinant of P times the determinant of B times the determinant of P inverse. And now we can use one more property of determinants. We can write this as 1 over the determinant of P. And so we have the determinant of P, the determinant of B, and 1 over the determinant of P. And now these two cancel. And so we're left with the statement that the determinant of A is equal to the determinant of B. And that's what we wanted to show in part A. Now in part D here is very similar. It's going to have a very similar flavor to this, but we'll have to do a little bit more work up front. We want to show that A and B being similar means that they have the same characteristic polynomial, and that's just a slightly more sophisticated calculation of the same type. Now let's dig into that one a little bit. So this is part D. All right. Now to calculate the characteristic polynomial of A, I have to first calculate A minus lambda I, and then I have to take its determinant. So let's spend some time thinking about how we can rewrite A minus lambda I. Now, that's going to be equal to, of course, using similarity, P times B times P inverse minus lambda I. But we can write this as P times B times P inverse minus P times lambda I times P inverse. Because this is just the same thing as lambda times P inverse, and P times P inverse is just the identity matrix. So this is equal. These two parts are equal, and so these two parts are equal. And now, what I'm going to do is I'll do 2 factorizations. First, I'm going to factor P out on the left, and then in the second factorization, I'll factor P inverse out on the right. So factoring out on the left, we can write this as P times B P inverse minus lambda times I times P inverse. And so we can see that these are the same just by redistributing the P. And now we're going to factor P inverse out on the right. Okay? And so what we've shown is that A minus lambda I is the same as P times B minus lambda I times P inverse. In other words, A minus lambda I is similar to B minus lambda I. Now, the rest of the calculation is very much like what we just did here. We're going to take determinants of both sides and set them equal to each other. We'll use the fact that the determinant of a product is the product of determinants, and we'll use the fact that the determinant of P inverse is the reciprocal of the determinant of P. So here's what we have. I'll do it in a couple of steps. We have the determinant of A minus lambda I is going to be the product of these determinants. Okay, and then we'll use the fact that these two are reciprocals, so they multiply to 1. So this is just going to be equal to the determinant of B minus lambda I. And this is the characteristic polynomial of the matrix A, and this is the characteristic polynomial of the matrix B. And so what this is showing is that A and B have the same characteristic polynomial. And so that fulfills the requirements for part D. Now the last part is actually quite easy. Now that we've done all the work in part D, we have to show that A and B have the same eigenvalues. All we have to do is remember that when we're looking for the eigenvalues, we're looking for the roots of the characteristic polynomial. So since the determinant of A minus lambda I is equal to the determinant of B minus lambda I, they're both going to be equal to 0 for exactly the same values of lambda. In other words, they will have exactly the same eigenvalues. So the eigenvalues of similar matrices have to be the same. Now the proofs of the other parts are very similar, and I will let you explore those on your own. I would encourage you to go in and try to prove some of the remaining parts of Theorem 4.22. It's very interesting. Let's head back to the class notes. Now, Theorem 4.22 can be used to show that a pair of matrices are not similar. And here's an example. Let A be this 2 by 2 matrix with entries 1, 2, 0, and 1, and let B be this 2 by 2 matrix with entries 1, -1, 1, and 2. Now, I want to prove to you that A and B are not similar matrices, and the proof is actually pretty simple. The determinant of A is clearly equal to 1. And the determinant of B is equal to 2 plus 1, or 3. And since the determinant of A does not equal the determinant of B, A and B cannot be similar matrices. Now, this draws a conclusion to the first part of our lecture on section 4.1. So join me again for the second part of our lecture on section 4.4 when we take up the all-important topic of diagonalization. Until then, take care. Bye-bye.